Hey everyone, so for today's lesson, I am going to talk about gravitational force, talk about circular motion, specifically uniform circular motion. Then we're going to talk about the equation for orbital speed, and at the end, we will talk about Kepler's third law of motion. So let's get started. All right, so the first thing is gravitational force. So what is gravitational force? It is the force that pulls an object, pulls objects with masses towards each other. Okay, so like Earth applies gravitational pull on us. At the same time, we apply gravitational pull back on Earth. Those two pulls are exactly the same from Newton's third law of motion. So the same thing applies to when we're working with bigger objects, like if you are thinking about moon and Earth, Earth and sun, a satellite around the Earth and Earth, or like any two objects, okay? So the letter that we are going to use for gravitational pull is F subscript G. Gravitational force is also called the weight of an object. Okay, so what are the variables that gravitational force depends on? So, well, first of all, here is our object of mass 1. This is object of mass 2. The distance between them, measured from center to center, is r. Okay, so the gravitational force between these two objects will depend on the mass of object 1, mass of object 2. It also depends on how far those masses are. Okay, it is directly proportional to the masses and inversely proportional to the square of the distance between them. Remember, the distance is measured from center to center. Okay, so if I combine those equations, those proportional relations into one, I will get gravitational force is directly proportional to m1, m2 over r squared. If we convert that into an equation, we would have to introduce proportionality constant. In this case, we have uppercase G as proportionality constant. All right, so what is this uppercase G? Well, the uppercase G is called the universal gravitational constant. Do not confuse that with lowercase g, which is, you probably have studied it as acceleration due to gravity. Okay, these are two different things. So uppercase G, its value stays constant no matter where you are. And the value is 6.67 times 10 raised to the power negative 11. All right. This value will be given to you on the AP reference sheet, so you don't have to memorize it. All right, so that's for gravitational force. Okay, then the next thing we're going to talk about is a field strength. So there are three types of forces that you probably have studied in your earlier physics classes. We have three non-contact forces: gravitational force, electrostatic force, and magnetic force. All three forces produce a force field around them. Okay, so non-contact forces create force fields, which is the space around the source object. So the source object is what you are actually working with, and then test object is what you're bringing into that field. So if we are thinking about Earth and a satellite around Earth, we would treat Earth as the source object and the satellite as a test object. Okay. The strength of the force field can be calculated by using the below relationship. So the field strength for any force is equal to the force, and that divided by the quantity that produces the force. Okay, so like in case of electrostatic force, the electrostatic force is produced by the charges. So the electrostatic field strength will be equal to electrostatic force divided by the test charge. Okay, in our case, we are going to work with gravitational field strength. So that strength is going to be equal to gravitational force, Fg, that we talked about earlier, divided by the mass, because masses produce gravitational force. Now, in this case, the mass is going to be the mass of the test particle. Okay, so if you are thinking about the gravitational field strength experienced by a satellite around Earth, the satellite becomes your test particle, Earth becomes your, not particle, sorry, test object, and Earth becomes your source object. Okay, so then the field strength experienced by the satellite will be the gravitational force divided by the mass of the satellite. Okay, Let's move on. So we know that gravitational force written as F subscript G, mass for test mass, and it is actually lowercase g that you have been using as acceleration due to gravity. Okay, it's actually gravitational field strength. Okay, and it does change with different masses. And it also changes with how far you are from the source mass. Okay, the units of field strength are going to be Newton per kilograms. Okay, and if we compare it with the earlier equation, so Fg equals G m1 m2 over r square, when you divide that by your test mass, you will end up with just Gm over r square. And the m in that equation is going to be the mass of the source mass. Okay. All right, let's move on to the next thing, which is uniform circular motion. So a few things. The simplest case of circular motion, so that we are going to talk about. So AP only works with uniform circular motion for this chapter. Okay, is when an object is going around a circle at constant speed. Okay, so where an object travels a circular path at a constant speed. Let's move on. For the sake of simplicity, we will treat all orbits, because you will be seeing questions where it's like a satellite around Earth, moon around Earth, Earth around sun, a planet around a star, a satellite around a planet. Okay, so for those, we are going to treat those orbits as circular orbits. Okay, and we are going to treat the motion as uniform circular motion, which means going around at a constant speed. Okay, so for an object to exhibit uniform circular motion, it must accelerate. We know that if the direction of the path changes, the object must accelerate, even if the speed stays constant, right? Now, for circular motion, that acceleration is called centripetal acceleration. Okay, the equation for that acceleration is v squared over r. That's what centripetal acceleration is. Speed is v and radius is r. Okay. All right, so from Newton's second law, we know that net force must be equal to mass times acceleration. So for circular motion, that acceleration becomes centripetal acceleration, and the net force becomes centripetal force. Remember, centripetal force is not a type of force. It's not like tension or gravitational force. It's just the name given to net force for circular motion. So that force will be equal to mv squared over r. Okay. All right, let's move on to orbital velocity and Kepler's third law. So when you're deriving an equation for Kepler's third law, through that equation, you also derive an equation for orbital velocity. So orbital velocity is just how fast something is orbiting around another mass, okay? All right, so things that you must know before you can derive this equation is you must know Newton's second law of motion, you must know what gravitational force is, centripetal force, uniform circular motion, you must know what it means by period of a repeated motion. You must know free body diagrams too, okay? So these are the equations that you will need to derive this. So you're going to need your gravitational force equation, centripetal force equation. You're going to need your Newton's second law equation. You're going to need to know that circumference of a circle is 2 pi r. And you also need to know that speed is distance over time as long as speed is constant. Okay. All right. So here is a question that we're going to work on. And that question helps you derive the relationship. So we have a satellite of mass ms revolving around a planet of mass mp. The distance between them is uppercase r. The satellite is revolving around the mass at a speed of v. All right. Derive an expression that relates the distance r with the period p of the satellite. Okay. The only variables that you can use are all of the above variables excluding v. Okay, so you can use ms, mp, you can use r, t, and that's it. And you can use the constants. All right, so let's start with, there's our satellite, we have our planet, okay, and those masses are labeled, the distance between them is r. If we draw our free body diagram, we will have our, and we're drawing free body diagram of the satellite, Okay, it's important to know which object you're drawing the free body diagram for. So for satellite, we know the only force acting on it is going to be the gravitational force, okay, and no other forces. And we know that from free body diagram, the next step is Newton's second law. We're working with a circular motion problem, so our Newton's second law equation is going to have acceleration as centripetal acceleration. Okay, so our net force, centripetal force, in this case, since we only had one force, that force will become the centripetal force. Okay, so that equation becomes Fg equals msv squared over r. Okay, we also know gravitational force has this equation. When you combine these two equations and you simplify them, you will end up with v squared equals gm planet divided by r. Okay, now this equation is the equation for orbital speed, so or orbital velocity. Okay, so you could be asked to derive this equation. So you should be able to do it fast. So practice this enough that you can do it really fast without spending too much time on it. Okay, so now we're going to move on to the original question, which is drive an equation between r and t. Okay, so the equation that we just derived doesn't have t. Also, we can't have v in our equation. So let's get rid of v. Let's find a relation between that speed and the period. Okay, we know the satellite is going around the orbit and the orbit is circular. We know speed is constant, and we know for constant speed, the equation is v equals d over t, so speed equals distance over time. So what's the distance covered by the satellite in a circle? It's the circumference of the circle, right? So 2 pi r, and the time it takes to complete that one full cycle is going to be the period. And then when you combine these two equations, all right, you will end up with this. And then after that, all you're really doing is just simplifying it and rewriting it. Yes, this. And that's your relation between a period of a satellite or a planet, whatever you're working with, and the distance from the source mass. Okay, and that is called Kepler's third law. And that is it for your lesson. Again, the derivation that we just did applies to any two celestial objects. Okay, so it could be any of these. Thank you so much for listening, and we are done with the lesson.